by talking, no problem. So let's start. So welcome to Analog Circuits course. I used to teach this course as a teaching assistant and also as assistant professor a couple of years ago. My name is Mustafa Abdelrahim. I just go by Dr. Mustafa. A brief history about myself. I took my PhD from a university called Egypt Japan University. So I studied between Egypt and Japan. I came here to US 3 years ago or 4 years ago in 2017 as a postdoc in Brown University. Then I joined Samsung for as an intern for 1 year. Then I joined New Mexico State University as a research assistant professor. It's just like postdoctor, but with another naming. Just last year. And now I'm an assistant professor tenure track in California State University, Bakersfield. A good one here is that when I came here in the first time, I was in Rhode Island, which is Eastern time. Then when I go to Samsung, it was in Texas, Central time. Then I go to New Mexico, which is Mountain time. And now I'm in Bakersfield, California, which is Pacific time. That's a good one. My research is in two fields. The first one is network on chips, which is basically the network that connects the cores in a multi-core processor. So I assume all of you has computers, and these computers has processors. And nowadays, all the processors has many cores. So they can run many loads in parallel. The network that connects these cores together is called network on a chip. My second field of research is called power and thermal modeling and management of also multi-core processor or many core processors. So let's keep going. These are some instructions and guidelines for this course. So the lectures is actually asynchronous. So attendance is not required for the lectures, but for the labs, it's synchronous. So you must attend the lab. All lectures will be, of course, recorded and published, in Zoom, or also I have a YouTube channel, so you have two options for this. The grading, we'll have 4 items for grading. Assignments is 25%. Labs, I mean the assignment of the labs, attendance and so on, is also 25%. The midterm is 25%, and the final is also 25%. Late assignments will be marked just by half of the max. So, for example, if some assignment that has 10 marks and you submit it late, it will be graded out of 5, not 10. My office hours, which is now Zoom hours, is every Thursday between 3:15 to 6:15. But just email me first, because sometimes we may have meetings with the department in that time. But this is, not quite often. So the background needed for this course is actually some little physics, very little. Okay, and basically the circuit theory that you studied before, like Ohm's law, Kirchhoff voltage law, Kirchhoff current law, Thevenin equivalent, Norton equivalent, AC circuits, of course, and the knowledge about inductors and capacitors. The text box, we have 2, but we'll focus on the first one, which is fundamental of microelectronics. This guy in here. Let me show it more clear. This guy. And I have the second edition, but if you have the first edition, it's okay. I don't see any big differences between them. And if you search on the internet, you can download it. The second one is Microelectronic Circuits by Professor Adel Sidra. He's, by the way, Egyptian. He's living in Canada right now in Waterloo University. But as I said, basically we will work from the first one, the fundamentals of microelectronics by Behzad Razavi. He is in University of California at LA. So the first assignment, just to cover the background needed, as I said, just read chapter 1 from Razavi's book and solve the exercise just after example 1.9. So in chapter 1, there is example called example 1.9. You will find just one line after this example, just to solve this exercise. And the deadline is just next week, Tuesday, 10 a.m., September 1st. Okay. So why analog circuits? Basically because traditional circuit elements that we have before, like inductors, capacitors, and resistors, are not capable of doing many applications that we require in this life. So for example, using these three circuit elements, which we just studied right till this moment in engineering, I assume that, cannot amplify signals. So let me explain here what amplifier means. So amplifier means it's just a circuit that has some input, for example, sine wave, and the output will be an amplified version of this wave. The same wave ideally, but amplified version. We cannot have electronic on-off switch. Yes, we can do that using relays, which is based on inductors, but they are very bulky, they are heavy, consume a lot of current. So we need a better solution. We cannot make AC to DC conversion. And what is this? Actually, if you have, basically you generate in life by nature from, for example, hydraulic generators, we generate AC signals, like sine wave like this. But for many applications, we need DC signals or DC currents. So this AC to DC conversion circuit is just a circuit, like for example, have an input sine wave like this, but the output will be a constant voltage, DC, ideally, again. We cannot have, for example, wavelength detector circuits. So for example, if you want to make a digital camera, you need a circuit that senses the incoming light, if it's red, green, blue, or whatever, and convert this, wavelengths or electromagnetic wave into voltage, so that we know what's the incoming light. So in principle, we can make digital cameras. We cannot do that using resistors, inductors, and capacitors. And we cannot make logic gates. Logic gates, you know, of course, logic gates and or not all such stuff, which is basically the computer in front of you. We cannot make logic gates using inductors, resistors, and capacitors. So we need something else, which is, of course, semiconductors, as I will explain later. But just a quick introduction, how to amplify signals. So in principle, just to have a quick overview or expectation of what we're gonna learn in this course. How to amplify signals, we need a resistor that can change using the input signal. So the input signal, which is small, and we want to amplify it, can change the value of this input, resistor. So the circuit in front of you is not a real circuit. It's an equivalent circuit of another circuit, but this is the equivalent form of it. And as you see here, the resistor here is dependent on V input. So it is 0 if V input is less than 0. And it's equal to 5,000 V input if V input larger than or equal to 0. So let's assume that V input, let me write here something. V input is equal to 0.01 plus 0.01 sine omega t, something like this. So, okay. So it's 0.02 volt peak to peak. So this is the input. So what will be R here? R will be equal to 5,000 multiplied by plus sine omega t. So I just removed the input here and put its value. So R here will be changed based on the input sine wave, which we want to amplify. Okay. How about the output? So let's go. Yes, oh, that's too far. So if we look at this circuit, the output is equal to VCC. It's just a naming. It's just a voltage, DC voltage. Just to forget about what is VCC, why is he call it like this, but just to forget about it, just a DC voltage, okay? It's a voltage divider, so VCC multiplied by R over R plus RB. RB is just a constant value resistor, okay? So this is equal VCC, and what's R? It's 5,000 multiplied by the input over 5,000 multiply the V input plus RP. Is this an amplified version of V input? I can say yes, approximately. So we can't have the ideal situation that we want to amplify signal. So the ideal situation is just multiply this signal by some value, constant value. We don't have such, we always have some distortion. Okay. So let's see if we run some MATLAB code just to verify this equation and see the shape of the output versus the shape of the input. Let's see that. So this is just a little MATLAB code that I did just to simulate the two equations that we see. Okay. So I assume that the time is changing from 0 to 10 with a step size of 0.001. Omega is it named by multiplied by 1. Very simple one. And VCC is this DC voltage that I just said, just forget about its naming. Why is it called VCC? Assume it's 1. And I assume RB is equal to just 100 ohm. So in that case, it's 100. Okay. And the input, as we see, is just, as I said, 0.01 plus 0.01 sine omega t. And this is the output, as we just derived it right now. It's equal to VCC multiplied by R over R plus RB. So let's draw the input, or plot the input, and also plot the output and see. Wow. So, yes. So look at here. This is the input, very small, and this is the output, right? So it's an amplified version of the V input. Okay, and you can play with the amplification or the gain, we can say, by changing VCC. Let's make it 5 and see what will happen. So hey, the gain, yes.
We're just seeing the one note notes, but not the MATLAB. If you're want to display that, we're not seeing it.
Okay. So maybe I shared the screen of the one note only, not the screen itself. So let me stop the sharing for a moment and reshare the screen. Can you see the MATLAB right now?
Yeah, we can see it now.
Good. So please, guys, if you have some problem like this, Just, you know, because I almost explained the whole example. Okay. Anyway, that's no problem. So I can explain it again. So what I'm doing in this MATLAB code, which is not required from you, I'm just here explaining why we have, if we have some special type of resistor, we can have some amplification. So what I'm doing in here, I'm just simulating these equations, okay? So I put the value of V input, the value of RB, and the value of V output as an equation, and just plot the two equations, the V input and the V output. So to plot it, we need a series because MATLAB is, of course, draw points. So I assume here T as a series, T is a time from 0 to 10 with a step of 0.001, okay? And this is omega because we have this omega in the equation of V input. It's 0.01 plus 0.01 sine omega t. Omega is just the frequency, okay? So I assumed very simple.
Do we have to write this down?
What?
Do we have to write this information down?
I can't understand.
Like whatever you're showing in MATLAB, do we have to write all these texts down, or will we get to it during the lab?
I didn't understand the question. You can write it in the chat and I can read it, then answer you. I couldn't understand. I'm very sorry. Just write it. Write it in the chat. I will check it now.
Yeah, quick question. So basically, is the first homework based on reading chapter 1 and doing exercise 1.9? What else?
What? If you do the exercise, what?
I'm saying for the first assignment. I think you said read chapter 1, do exercise 1.9, and what else?
Just it.
That's it, right?
Yeah, so read chapter 1 and solve the exercise after the example. Okay?
Okay. And where do we submit it? In Canvas?
Yes.
Yep, thank you.
Okay. Okay, so this is the input and this is the output as we derive it here from one node. So this equation. And let's just plot them together. So if we plot them together, this is the out, this is the input, this very small signal, and this is the output. And we can control the amplitude of the output using VCC. So with VCC is equal to 5, we have here maximum of 2.5. If we make it 1, it will be, of course, less. See? It become 0.5. It's just divided by 5. Okay? So this is in principle how we can make an amplifier. What is the idea behind amplifier? We need a resistor that can change, that its value can change using the input. The input signal that we want to amplify controls the value of resistor. Okay? Okay, how can we sense the light? How we can make a digital camera? Again, we need a special type of resistor. This resistor now, is it changing or can be controlled using the wavelengths of the incident light? So, for example, if you have a red laser beam incident on this resistor, it will have some value. If you have a blue laser beam incident on this resistor, it will have another value. So in principle, the out here, which is just equal to VCC multiplied by R over R plus RB, is also function of the wavelength of the incident light. Okay, guys? So this is a quick introduction about why we need analog circuits. So what is the magic that will do all of that is actually semiconductors. So semiconductors is actually the material that will enable us to make new devices other than resistors, inductors, and capacitors. And these new devices that we're gonna study in this course have such kind of properties that I showed you, resistors that can change with wavelengths, resistors that can change using the input voltage, and so on and so forth. So let's get started. And unfortunately, we need some physics, but it will be a very brief physics. Okay? So everything started by something called Bohr's model. Of atom. Bohr is the name of a person. He was a scientist, one of the greatest physicists in the last century. And this guy said that, or theorizes, or imagines that any atom is actually a nucleus, and there are some shells around the atoms, around the nucleus, I'm sorry, that has electrons. Okay? Very basic stuff. Okay, so we have, based on that model, we discovered that there are two types of materials, we can say. Active materials that can make interactions with other elements. And we have, for example, something like noble gases that doesn't interact with each other. And why those do that and those do that? Because of the distribution of electrons around the nucleus. So for noble gases, for example, let's assume the helium atom. It has 2 electrons. So we have the nucleus here, and we have just one shell, and this shell has 2 electrons. And the first shell, if it has 2 electrons, then it's complete. So helium as a noble gas cannot interact with other elements. Okay? Neon as another example. Has 2 orbits. The first one has 2, the second one has 8. So it's also filled, the outer shell is filled, and it cannot interact with other elements. Elements like sodium, Na, has 11 electrons. So we have the nucleus here. Then we have 2 electrons in the first shell, 8 electrons in the second shell, and just 1 electron in the third shell. And this shell, to be, minimized in energy, it has to be either 0 or 8. So sodium usually donates this electron to other element, like for example chloride, to make a bond. Okay. Now let's go to the third type of elements, which is semiconductors. Semiconductors, they don't have a filled outer shell or partially filled or less than half of the outer shell. So usually they have 4 atoms in their valence band. This last shell is called valence shell or valence band. They have 4. They are not like sodium or copper, for example. They have less than 4, 1, 2, 3. Or they're not like helium, which have a complete filled outer shell. So what sodium usually do, what semiconductors usually do, like for example, silicon or carbon, okay, or gallium arsenide, germanium. All these semiconductors has the same properties. They have 4 electrons in the outermost shell. Okay, so what they do, they form what's called the covalent bond. And what's covalent bond? It's very simple. So you have a silicon atom surrounded by 4 silicon atoms. And each one will donate 1 electron. So This one in the middle here, we will see not 4 if it's isolated, it will see 8 electrons. And of course, the other one's the same. So this will be spread in all the atoms inside the material. So each silicon atom or each semiconductor atom in general will form this covalent bond with 4 neighbors that around it. Each one will donate 1 electron, so it will see 8 electrons instead of just 4 electrons. Okay. So how about the conductivity of silicon? So sodium has 1 electron, copper has 1 electron in its valence band. Okay. So this electron is loosely bonded to the nucleus, so it can easily, navigate if there is a potential potential voltage acts on the material. But how about the silicon? If we have a sample of silicon like this, and we apply a voltage on it, will it conduct? It depends. It depends on what? On the temperature. So based on that very ideal shape or crystal, this is called the crystal structure, okay, or covalent bond. At temperature equal to 0 degree Kelvin, this ideal, structure will hold at that temperature, and the current will be 0. Silicon will not conduct at 0 degree Kelvin. Okay. Also, at higher temperatures, some of these electrons in here can lose or go or leave the bond and become loose, and can conduct or contribute to the conduction current. Okay. So let's go. So let's now study the conductivity of silicon. Okay, we just said that at T equal to 0 Kelvin, it will just behave like an open circuit. I'm very sorry. So at T equal to 0 Kelvin, silicon will be just, just like insulator. No charge carriers. No free electrons. At room temperature, which is approximately 300 degree Kelvin, silicon can conduct. So what's really happened? So in simple terms, these bonds will lose electrons. So for example, the electron that was forming this bond here will be loose. Okay. Also, Bohr model that we just explained, simple nucleus and with shells, doesn't explain really much what really happened in that situation at room temperature. So we go to another model, which is the modern physics, solid state physics, so based on quantum mechanics. So based on the modern theory of quantum mechanics, we can envision, we can imagine the internal crystalline, or the energy bands or energy shells, okay, of these electrons in the following way. So we can envision the silicon in that manner. So remember, Bohr model says that we have a nucleus and we have shells around, right? The modern quantum mechanics theory will say something similar, but we'll explain it in another way. Okay, so they said that we have what's called energy valence band. And what's valence band? It's just orbitals, just like these ones, but completely filled. Filled with electrons. And we have above here what's called conduction band. Okay? And in between, we have something called energy gap. Energy gap. In simple terms, this energy gap is just, you know, a space that doesn't have shells, doesn't have orbitals. So, and the electrons cannot only be in orbitals. They cannot be just in, you know, in free space. So there should be an orbital energy, what's called energy level. So that this is just the home of the electron. So here we, in the valence band, in this area here, we have orbitals like this. So electrons can be there. In the conduction band here, we also have orbitals like this. So the electron can also go to the conduction band. In between here in the energy gap, we don't have orbitals, so it's forbidden for the electron to be in this area here. Okay? So from the naming here, it's very interesting that this called the conduction band means that if you find an electron here in this band, then it can contribute to the current. So what really happened at room temperature, some of the electrons here, let's draw with another, some electrons here gain energy from the temperature, because temperature is just thermal energy, and go to the conduction band. And once you have electrons in the conduction band, then you can have current. If you applied voltage, you will have a current. Okay? Any questions?
Not so far.
Good. Okay, so this is the what's called energy band diagram of silicon. This is called, or semiconductor. Okay, energy band diagram. Can we also draw a similar band diagrams for other elements like insulators? Yes. So for insulators, it is the same. It is basically the same. It should be basically the same. So, or let's just change the code. That's fine. So for insulators, you'll have the same stuff. You have also valence band, just an orbitals filled by electrons, and you have conduction band, orbitals that doesn't have electrons at 0 Kelvin, and in between bigger energy gap. So just to see the difference here. Here is the same, exactly the same. The semiconductor and the insulator is exactly the same structure. Also, the energy gap for insulators is way larger than the energy gap of semiconductors. Okay? That's why at room temperature, insulators, okay, like for example, wood, cannot conduct current, because the thermal energy that comes from the temperature is not enough for electrons in the valence band to go to the conduction band. They cannot make it. The thermal energy is less than the energy gap of the insulator. Okay? And by the way, some semiconductors also have also a larger energy gap. So the energy gap is actually a property of the material. Okay, so for some materials this is a small. So for example, for germanium, which is a semiconductor, the energy gap is equal to 0.66 electron volt. Electron volt, by the way, is just another unit for energy. Something equivalent to joule, okay? And to convert from electron volt to joule, just multiply by the electron charge, which is 1.6 multiplied by 10 to the power minus 16. So don't worry about the electron volt. We will use in this course electron volt oftentimes because it makes the number, you know, easier to understand and easier to comprehend and easier to remember. Okay, if we just say it's 0.66 multiplied by this number, it will be ugly. Okay, so electron volt is just another unit for the energy, just like joule. Okay, so for germanium, the energy gap is 0.66 electron volt, or 0.66 multiplied by 1.6 multiplied by 10 to the power minus 16 joule. For silicon, the energy gap is around 1.2 electron volt. And for carbon, which is also semiconductor, the energy gap is equal to 2.5 electron volt. So if we draw the energy band diagram of all of those guys, this is germanium, this is valence band, this is conduction band, this will be silicon, and this will be carbon. Way bigger. That's why we mainly use silicon and germanium to make, you know, the devices that I just talked about, because it's easier to handle. They don't need a lot of energy to conduct. Okay, that's very good. So how about, just to complete the picture, how about conductors? What is the energy band diagram for conductors? Does they have energy gap? Actually not, because they are conductors. They are super in that. So we have the valence band, and just on top of it, the conduction band. So it's very easy for an electron here to go to the conduction band, so that the conductors are good conductors, of course, like metals, for example. And sometimes they even intersect. So even at zero degree Kelvin, they can conduct current. So for some other conductors, the energy band diagram is actually something like this. This is the valence band, and the conduction band is actually intersected with the valence band. So there is intersection. So even at 0 degree Kelvin, they can conduct. That's why we have superconductors. Okay. So that was, yes. One last thing. Now we know that, let's go back to the blue. We know that silicon can conduct based on temperature. So pure silicon, the silicon found in nature with, you know, with no impurities, no other atoms. So if you pure silicon, I mean by pure silicon, just silicon. If you take a material of pure silicon, you will find all the atoms in this material is just silicon. There is no other atoms from other material. Okay. So we just knew or understand that silicon can conduct, but based on the temperature. Some electrons gain some energy from the thermal energy around and go to the conduction band. How many electrons that does this at room temperature, for example? So let's assume that the carrier density per unit volume, let's call it N. So what is N? N is the number of carriers, number of electrons that can conduct the current. I mean, the electrons is the conduction band per meter square, per meter cube, or centimeter cube. So in this course, because usually we have very simple devices, very small devices, we usually use centimeters cube, not meter cubed. Okay, so let's add C here, per centimeter cubed. We knew that this guy here dependent on temperature and also the energy gap. So if you have a small energy gap, you expect more electrons in the conduction band. And if you have a higher temperature, you also expect more electrons in the conduction band. So this guy N is actually a function of both T and energy gap. And there is a kind of derivation. You can just go to any silicon, solid state physics book, and you can find this derivation that N is equal to some constant 5.2 multiplied by 10 to the power 15 multiplied by T to the power 3/2 exponential minus EG over 2KT. What is T? T is, as I said, the temperature in Kelvin. This is very important. It's not in Celsius or Fahrenheit or whatever, just in Kelvin. In this course, everything is Kelvin. K is Boltzmann constant. Don't try to memorize it in the exam or whatever. I will just give you the value. Okay, and as I said before, EG is the energy gap, which is a property for the material. Each material has its own energy gap value, and T, of course, is the temperature. And as you see here, N is proportional to T, actually T to the power C/2. I mean, if T increases, N will increase. How about the relation between N and EG? Is it a direct relation? If EG increases, N increases, or the opposite? Let's try. If you put EG here equal to 0, so this will be exponential 0. So N at EG equal to 0 is equal to 5.2 multiplied 10 to the power 15 T to the power 3/2, and the exponential 0 is 1. If EG is equal to infinity, which is something, of course, not practical, but let's assume for for the sake of argument. So 5.2 10 to the power 15 T to the power 3/2 exponential minus infinity. And the exponential minus infinity is what? It's actually 0. So N at EG equal to infinity is equal to 0. So N is actually disproportional to EG. Okay? If EG, it's just for correctness, let's do it another way. It says that if EG increases, N will decrease. And that's, of course, obvious. If you have larger energy gap, less electrons can do it to the conduction band. Okay, so far? Any questions? Good. the current carriers in semiconductors. So till this moment, we are talking about pure silicon or pure semiconductor. And we talked about electrons that lives in the conduction band can conduct current. Okay? Actually, there are, this is special for semiconductors, there are other type of carriers that can conduct the current. Okay? So let's have the covalent bond again. So we have silicon, silicon, silicon. Good. Let's assume that we are now at room temperature and one of those naughty guys, the electrons, has left the bond, its bond. So, yeah. Okay, that's enough. Okay, so there is missing electron here in this bond. This is assumed for at t equal to 0. I mean here by t is the time, okay? So let's assume the time at that point is our reference is 0. At another time, let's say after, for example, 1 microsecond, what will happen is that one of these electrons can leave its bond and go and fill this bond again. So let's assume this guy will do that. So silicon, silicon, silicon. This guy will be filled. Let's use another. So this will be filled. Okay. Let's go back. And this will be, you know, not filled again. So this bond now is lost an electron and it needs the electron to stabilize. So we have here, yes. Okay, this is, for example, t equal to 1, whatever. It's just a snapshot. Okay, then let's assume that this electron in here will go and fill this hole again. So at t equal to 3. So this guy was filled. So yes. Good. Wow. So look at the movement in here. So we have electrons that moves from here to here. Then another electron that moves from here to here. So actually the losing electron to the conduction band will leave behind what we can call a hole, some gap, okay? And this gap will attract other electrons to it. Actually, what happens is that these electrons that moves from a hole to hole or from a bond to hole is gain some energy. This energy is little, is not enough for it to go to the conduction band. So it just go to another bond in the silicon structure or silicon crystal, we can say, or silicon material. Okay. So we have two currents now, a current in the conduction band and another current that fills these holes in the valence band. So we have two currents. And it was more convenient here. Historically, it was more convenient for scientists to model this as if it was a positive charge, okay, that moves. So the electron actually moves in this example in that direction. This is the movement of electrons. So the scientists, along the years, it was more convenient to them to assume it or model this as positive charge or what's called holes that moves in the opposite direction. And they call it holes, P. So we have two carriers now for the current. We have electrons and we have holes, but just have some caution here because this hole is actually a model. What's really happening is a movement of electron. Okay, it's just a model. Okay, something that we can model the real world in that way. Okay, so we have two. We can say we have two energy current carriers: the electrons in the conduction band and the holes in the valence band. Okay, so we have two carriers. The first carrier is the electrons, and their density, we call it N. And we have the holes, and we will call their density P. This is electron by centimeter cube. This is hole by centimeter cube. Okay? Good. Very good. So a question here. We know that, let's go back to the red, that N is equal to 5.2, 10 to the power 15, T, 3 over 2 exponential minus EG over 2 KT. How about electrons? How about the density of holes? Should be similar, should be larger, should be smaller? What do you think? Anybody has an answer? So the question is as follows. Do you think that P, the density of holes, is larger than N, smaller than N, equal to the N? Any answer? Any guess?
Smaller than?
Why?
Is it related to material?
So let's go and think about it. If I'm asking the question, the same question, but in another way. If you found in nature a piece of silicon, pure silicon, okay, what do you expect? Do you expect that it has more electrons than holes, or holes more than electrons, or equal? If we have electrons more than holes, that means you found a negative charge, okay? Something that has net negative charge. If it has holes more than electrons, it has more positive charge, okay? So basically, when you find something in nature, you find it neutral. What means by neutral? The number of electrons is equal to the number of holes. And let's go to the basic principle. What creates hole in the first place? An electron that leaves the valence band and go to conduction band. So if this is the valence band and an electron go here to the conduction band, okay, so we have one electron and we have one hole. So basically they are the same, because holes comes from what? Comes from an electron that leaves the valence band to the conduction band. So we expect N to equal to P. So P is also equal to 5.2, 10 to the power 15, exactly the same equation. Okay? And even by sense, if you find a silicon in nature, you will find it neutral. Okay? Does this make sense?
Yeah, that makes sense.
Good. Okay. So okay, so we knew now that until this moment, the only way to increase the conductivity of silicon, for example, is by increasing temperature. If you increase temperature, for example, if you have silicon and you wanna this silicon to conduct more, you can only do that by increasing the temperature. You can do that by increasing, or I'm sorry, decreasing the Eg, because this is a property of the material. You can't change it. Okay. But I just forget one thing before we go forward with the increasing the carrier density. Yes. Another question here. Is silicon poor conductor?
Hello.
Or bad conductor?
What is your father's first and last name?
So a question here. What do you expect? Is silicon a good conductor or bad conductor? Any guess?
Bad.
Yes. Why?
It should be a poor conductor because pure silicone is, like you say, insulator.
Yes, that's right, because it's similar to the insulator because it has energy gap, although it's smaller. Okay, and we can actually prove that. So we knew that N is equal to that equation here. If we put T equal to 300 degree Kelvin, which is the room temperature, and we know Eg for silicon, we just mentioned it, is 1.2 electron volt. If we compensate in this equation here, N equal to B equal to 10 to the power 10 electron or hole or per centimeter cube. So we know that for each 1 centimeter cube, there is 10 to the power 10 carrier. Okay? But how about the number of atoms itself in 1 centimeter cube? The density of the atoms of silicon itself. So the density of atoms of silicon per centimeter cube is actually 5 multiplied by 10 to the power 22 atom per centimeter cube. So we have 10 to the power 10 carrier per centimeter cube, but we have 5 multiplied 10 to the power 22 atom per centimeter cube. What does that mean? That means that each 1 multiplied by 10 to the power 12 atom contribute by just 1 electron to the conduction of current. 1 multiplied by 10 to the power 12 mean 1 trillion. So for each 1 trillion atom, only 1 electron is generated. Okay, that, for example, if we compare this to sodium, sodium is almost 1 to 1. Each atom contributes one electron. So it's a very poor conductor. Okay, and this is a very brief proof for it. Okay, now let's go back to the question. We'll just finish in 10 minutes. Okay, how to increase the conductivity of silicon. But before that, any questions so far? Don't be shy. Ask anything in any part of the lecture. Even at page 1. That's right. That's fine. Okay. If you have question, guys, just email me or prepare it for the next lecture, and you can ask before I start lecturing in the next lecture. Okay. Okay. How to increase the conductivity, and by meaning conductivity, the carrier density of silicon. Using this equation in here, we have only one parameter, that we can control, which is the temperature. But this is very costly because you will need energy. You need to heat up the silicon, and this heating, of course, consumes energy. But actually, there is a good trick that you can do to increase the carrier density of silicon, which is doping. So what's doping? Doping is the operation by which we add some impurities to the silicon. So we assume that the silicon material that we have right now is pure. I mean, all the atoms in the material we have is just silicon. And when we make doping to the silicon, we put another material, another atoms from other material to the silicon. And we do that in two ways. I will explain one way now, okay? The first way for doping is by adding atoms of materials that have 5 electrons in their valence band. Okay, 5, not 4, 5 electrons. Silicon has 4. I will now add using some process. We don't care about it right now. We will add some atoms that has 5 electrons in their outermost shell. So what will happen? One example for these atoms is phosphorus. P. So this is a silicon, atom of phosphorus, silicon. This is what will happen. Four electrons out of the 5 that the phosphorus has will contribute in the covalent bond with the neighbor silicon atoms, and 1 electron become free. Okay, so the phosphorus has 5 atoms in its outermost shell. 4 of them will make a covalent bond just like silicon with the surrounding atoms of silicon, and 1 electron will be left free, and this electron can contribute to the current. Again, how can we translate this in our energy band diagram? It will be very easy. This is the energy band diagram of silicon. We have here the valence band. You have here the conduction band. And what phosphorus will do exactly, it will add another energy level in the energy gap. So this energy level or shell or orbit, a new orbital, we can say, is created in the energy gap. Remember, I said that the energy gap has no orbitals, and the electrons should only move in orbitals. This is their homes. They cannot do, they cannot move in the crystal outside orbitals. So the phosphorus will add a conduction band, an energy level, a shell, an orbital very close to the conduction band. And what's meant by very close? It means that an electron here in the phosphorus atom will need very little or very small energy to move from this energy level to the conduction band. This is another interpretation for what we explained in here, but in a more formal way. Okay? So in the past, an electron needs 1.2 electron volt to move from the valence band to the conduction band. Now it needs very little energy to move from the conduction band, I'm sorry, this energy, this new orbital of phosphorus to the conduction band. But in that case, here, if an electron moves from the valence band to the conduction band, it will leave behind the hole. Here, it will leave a positive ion. Positive ion. So this is positive ion, which is phosphorus. So phosphorus atom, when it loses an electron, it becomes imbalanced because the number of protons, which is positive, is larger than by 1 the number of electrons in the phosphorus atom. So it becomes a positive ion. But this positive ion is very heavy. It cannot, contribute to the current. Only the electrons and the holes contribute to the current. Again, one last thing before I finish. Again, the material should be neutralized all the time. The number of positive charge should equal always to the number of negative charge. So in this new material, which is a silicon doped with phosphorus atom, what is the density of the negative charge? Is N. What is the density now of so this is the negative charge. The positive charge, it's B, the holes, and the newly created ions of phosphorus. And we call the density of the phosphorus atoms that we added to the silicon, we call it N donors. So this is because phosphorus donated an electron to the material, we call them donors. And ND here is the density of the positive phosphorus ions. Okay? So we'll stop here and we will continue next time, starting from another type of doping. So this is a doping with atoms with 5 electrons. We can do doping with atoms with 3 electrons. Okay? And we'll start from there next time.